All right, so I put a final question on the board. Somewhere while we were on break, somebody saw it, some of you didn't. Why electrify? And this isn't the greater political question, oh my God, we're gonna save fuel, all that kind of stuff. We're electrifying, adding a high voltage system to the car. Our main point of that is to drive a motor. So we can drive the car using electricity, right? That's really the point of all this. So somewhere at the end, our end goal is very big motor. The motors, really neat things. They are three-phase AC electric machines. Most of them are what we call a Y-wound machine. Looks like this. U, V, W. So we can go U, V, and W. And those are your inputs to your Y-wound electric machine. I believe U, V, and W are from generators in an industrial scale. Right? And then motors are actually X, Y, Z. So what do we have in the front of the vehicle? It's not a motor, it says so. It's a generator, but it does motor things. So it's not a motor, it's not a generator, it's both. We're gonna call it an electric machine in engineering terms. What am I gonna call it as a mechanic? It's the drive motor, traction motor, electric motor, main generator, whatever you wanna call it, right? We know those terms are interchangeable. We're all right with that? Okay, we'll come back to the electric machine. I said something kind of interesting with it. DC battery, three-phase AC. So, three-phase AC. So can I just hook the battery up to that motor and have motion? Absolutely not. Oh boy, the smoke that would come out of that thing, and fast, it would lock in one, oh no, thank you. So I have to have some way of going from this big fancy DC over here to this even fancier AC. And I think we know the piece of technology that we're going to use for that. What do we call that? It's an inverter, right? So, inverter, and its job is AC to DC, and DC AC. So it's a bi-directional electrical switch panel. Right? Can turn AC to DC and DC to AC. So far, neat. So we're going to draw the inverter on the board. We're going to spice up our life. We're going to make the inverter big too. Oh, look at that. Oh, yeah. Huge. And almost rectangular, maybe. My inputs to the inverter on the high voltage system. My inputs from the battery, obviously DC, right? All right, so we're going to have a ground. And we're going to have a positive. So a negative and a positive. Ground was technically wrong. So inside the inverter, those are our DC sections. What else do I need? So I need to take my DC, I need to make AC. I'm going to do that with a series of electrical switches. Does something mechanical react fast? Does that contact in a light speed relation act very quickly? No. In a refresh rate on a television, does it react quickly? No. So mechanical switches, out of the question. Can't use those. I'm going to use a little something we like to call an insulated gate bipolar transistor. They are a isolated gate MOSFET, metal oxide semiconductive field effect transformer. Does any of this stuff really mean anything to you in the long run? Not really. Insulated gate bipolar transistor, when I draw the symbol, that's the thing that's probably going to take you somewhere, right? So we're going to wire a set of them. There we go. Bottom to it. Oh, there's our controlled side of it. There we go. Boom, 2 switches, look at that. One side attached to positive, one side attached to negative. Can I close both those switches at the same time? What would happen if I closed them both at the same time? What if I attach negative and positive together at the same time? You have a short circuit. There's no load in that yet, right? Just the switches. And the switches, very, very low impedance. Okay? So we're never, ever, ever going to close both those switches. Just one. I'm attached to positive, or I'm attached to negative. Not both. So those switches, that pair, will drive one phase inside the motor. It'll drive U, V, or W. That's it, just one. Okay? So, how many sets of switches do I need to operate that motor then? So if I could, 3. So I need 3 sets or 6 IGBTs in total to drive an electric machine. All right, so let's keep going. We're going to finish our circuits here. Come down. Go. Down. This. You're like, wow, they're really close together. There will be a point to this. There we go. And then finally, we'll do our last IGBT set. So how come they're called insulated gates? Well, watch this. Ready for this? This is the trigger. Doesn't touch the switch. They're insulated. This is run through a gate driver that is connected to 12 volts. This is not 12 volts. This is 400 volts. So 12 volts gets jumped up to 300 volts to operate a gate that'll allow 1,000 volts through. But the 1,000 volts will never touch the 12 volt side. Make sense? Cool. Insulated gate. The gate doesn't touch the high voltage. Doesn't matter in the long run. Are you building these boards yourself? No. All right. So now we've got U, V, and W. We got to connect these up. How's everyone feel about pink, purple, green? I like these colors, don't you? All right, cool. So V seems pretty purple to me, so we're going to purple it up. W is going to be green, I think. Let's see how well that shows up. Oh, not too bad. And then U, we only got pink left. U feels pretty pink to me. We're going to hook this up to that inverter. So V, oh, that's the wrong color for V. V is going to go in. Jump this one. Jump this one. Reconnect it here. W, going to bring it in. Jump this one. Connect it here. And then our last one, U. Hey, U. We're going to bring it from here Had to drop it down a little bit, connect it right. Boom. All right, so far so good, right? If all of these are open, no electricity flows through, we can't drive the motor. The way that we're going to drive the motor is we're going to excite the windings in the motor. If we excite a winding of wire, it's going to turn into a magnet. The magnet is going to pull on the rotor and make the car move. Electric vehicles are actually magnetic drive. Neat, huh? We use the electronics to power the magnets to make them move forward. It's like a really, really advanced set of wooden trains. You know, the wooden locomotive couples to the boxcar. You pull the boxcar along. Well, the permanent magnet in the rotor is going to attach to the magnetic field generated in the coil. We're going to keep moving the magnetic field around. So it'll go UVW, 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 and that's what gives you your rotational motion. Neat. All right, so let's look at it electrically though. If I attach this to positive and I attach this to negative, what's this? Oh, I need that one and I need. So this is attached to negative. Is current going to flow into or out of that coil? Out of, okay, cool. Out of. If I attach this to positive, is electricity going to flow into or out of there? Into. Just like this. If I have electricity flowing into here, it's got nowhere to go. So it has to flow out of V. Huh. Then I've got W. W is just kind of kicking it old school there. Do I have to put electricity in or do I take it out? Does it matter? No. If I put it in, it's going to become, say, a north pole. If I take it out, it's going to be a south pole. What we do is we switch them in order to make them north or south, and north and south, and north and south. That's all we're doing here. North pole, south pole, north pole, south pole, north pole, south pole. Okay. So we've got our basic setup. We will come back to this later on. We'll let that marinate though, okay? All we're doing is controlling the current direction inside the electric machine. That is our AC portion. Is that real AC? Is the current really moving back and forth? Or are we just kind of changing where it's attached to? It's synthetic AC. It's fake. Drive it in one side, take it at the other. Then we use the same DC signal to drive it from the bottom and take it at the top. We're switching direction, AC, but it's not like the same as what comes from the wall. If we look, is there a connection between here and the load in the middle? Is a coil a load? There's resistance to a coil, right? Not very much in this case because I want lots of current. Is it attached positive? Is it attached negative? Is that a good circuit? Cool. Could I hook that up to a battery? Let's do it. All right. Let's do it. That looks awkward when you do it that way. So, here we go. I'm going to drop this down and you'll figure it a little bit later on why, but there we go. Oh, no, gotta make that connection. Okay. Sure. Good enough. We'll figure that out in more. Huh. Huh. Well, would you look at that, eh? Battery, drive motor. We're doing okay here. Do I really need anything else to electrify a high voltage vehicle? No, don't worry about the engine. I'm worried only about the high voltage side. Do I really have to add anything else to this high voltage side to have a hybrid car? What's that? Isn't that what that electric machine is an alternator? Oh, here, we'll make it an alternator. I love the fact that you brought that up because I forgot something in my diagram. Oh, do you mean for the auxiliary system? I liked it. I like it a lot. I like it more than you know. Oh, geez, that's a terrible diode there. I just gave away the answer to my next question. Those are all diodes, right? Are they pointing at positive or negative? Positive, right? All right. So they point at positive. They're used for regeneration. They're flyback diodes inside of the switch. But if you look at them and you remember all the way back to your alternator and starter course, they look a lot like a rectifier bridge. Diode trio, whatever you want to call it. How do I take my AC that's generated during regenerative braking and turn it into DC for my system? Them there diodes are part of the key. Any electricity that's generated can't exit through the diode. If I open up all of my IGBTs, electricity can't flow through there. It's only got one choice. It's got to get enough pressure to overcome battery pressure and go back to the battery. Alternators. So there's an alternator built into the drive motor. That's regen. But I've got another electrical system, right? Yeah? Could I run a normal alternator on the vehicle? I guess. Doesn't sound very efficient though, does it? So what do I do instead? I put a box in this system, right? Called a DC to DC converter. Yeah. So we'll draw our first box. This isn't a complete box, but that's okay. DC to DC converter. What's the job of a DC to DC converter? What does it do? What does it do? What does it replace? No. DC to DC converter. What does it do? Charges battery. The 12-volt battery, right? Okay. So it took the job of the alternator. A DC to DC converter is an alternator for an electric vehicle. Charges the 12-volt side. Cool. So, on this side here, we're going to need volts. We've seen one of these guys before. Hold on. Not every electric vehicle uses 12 volts. Some of them use 16, 24, 48. But it is lower than system voltage or lower than the high volt. Why do I need a 12-volt battery in one of these cars?
The low voltage controls the higher voltage.
Low voltage controls high voltage. That is like an A answer right there. Yep. The little battery, make sure the big battery turns on and off. Make sure all of the electronic brains in the car work. Make sure the PCM works. Make sure the hybrid control module works, the body controller. Why wouldn't I just run my heated seats on 400 volts? Because that is what we know as an electric chair, right? We don't want that. Imagine you go to turn on the radio and it gives you an 800 volt punch. Woo! That song really kicks. No thank you. So, we're going to have an auxiliary electrical system. What used to be our primary electrical system in a 12 volt internal combustion car is now going to be called an auxiliary electrical system. Okay, so 12-volt battery. Where does the negative post go on a 12-volt system? Whoop, whoop, whoop. What's that mean? Chassis ground, right? More than anything, that is chassis ground. That is not an earth ground. You see that lots in our electrical diagrams. Okay? So that goes to the chassis. And then, from the DC to DC converter, I get that's no good. Use this one that I was using before. We get 12 volts, 14 volts, whatever it is to charge the battery. He's fading again. Did you not do like a bump while you were out there or something? A little speed, caffeine, Monster Energy, 12-hour energy, 15-minute energy. No, nothing. You got nothing. Got it. Okay. So our DC to DC converter, we know its job is to charge 12 volt. Took over the job of the altmeter. If I have an electric car, how many things under the hood spin all the time? If I have an internal combustion engine, what spins all the time? Except for these new stupid stop-start vehicles. Ugh. I get into my 1988 Caprice, that of course is completely emissions compliant. I twist the key, it goes vroom, as long as it's making the what's turning? The crankshaft, right? If I electrify a vehicle, what do I take out of it? The whole engine, man. Let's come on, try. Yes, the crankshaft doesn't spin anymore, right? The entire point of it is, don't waste energy that we don't have to. Internal combustion engines. We get in trouble all the time. You can't let your car warm up. You're damn right I can. I live in Canada. It's cold, man. It's not for the car, it's for me. But it's inefficient, right? Electric vehicles, they only turn the driving mechanism when we want to propel the vehicle. So we don't have something to go blah, 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 blah. So if we don't have that spinning crank, we don't have a belt. If we don't have a belt, we don't have an alternator. So somehow I have to charge the 12-volt system without using a spinning device. Enter the DC to DC converter. And of course, this guy, if I'm not powering it off an engine, I must power it off of electricity. So, there we go, wire it here. And on the top side, we will wire it there, just like that. It is a high voltage system that charges a low voltage system. So far, so good.
I have a question.
Yeah, I mean,
I left my phone in my car on a really cold day.
yeah.
When I came back, my phone was overheated. Why doesn't that happen in a car?
It can. Except we introduce cooling systems and warming systems.
But it's cold outside and my phone overheated.
Well, I don't know why your phone would overheat. Was it plugged in? Was the screen on?
No, I just left it sitting on my
Okay,
seat.
then it had a temperature sensor issue. It shouldn't have overheated unless it was shorting out internally. The battery actually buckled and froze. It didn't swell up after, screen
No.
didn't crack. No, I got nothing. Not a phone tech yet.
Well, it's just because it's the same kind of battery, right?
Can be.
Lithium batteries,
So this battery setup isn't exclusive to lithium. We can set up a battery like this on a nickel metal hydride vehicle as well, right? So that battery configuration can be similar chemistry or can be very different chemistry. Regardless, your phone should know because at cold temperatures they do freeze, they don't overheat. For sure they freeze, right? And we'll get to that as well. I'll get to temperature challenges. All right, so 12-volt systems we're very, very familiar with, true? Or at least we should be at this point. If we're not, hey, maybe we'll find out something new. A 12-volt system works kind of like this, right? We know that we're not worried about the alternator, we've got that covered. But as far as a load goes, we go, you know, from our source, our batteries here, we're gonna come out of our positive cable, we're gonna go down, we're gonna go through some type of circuit protection, we might go through the load first or second, I don't care, right? We got our load, we've got a switch in the system usually, then it goes to ground. True? In order to make an electrical system work, it's all gotta be connected, right? But I put it to the chassis, it's gotta get back here somehow, true? It starts at the battery, it's gotta go back to the battery. On the vehicle, boom, we're gonna use the chassis. So, draw a race car here. It's a Civic SI from like the 90s or whatever. There we go. Realistically, what's actually happening is, goes through the body, goes back to the battery, right? What happens in this system if I get a short circuit right here? Gets hot, burns the wires, might burn the car down, cool. If I get a short circuit after the fuse, blows the fuse, cool. If I am leaning on the car and touch a live 12-volt wire, what happens to me?
You're dead.
A 12-volt wire? Like just a light bulb in a car. You've ripped apart a truck and you're holding onto a 12-volt wire and it's got 12 volts in it.
What is that?
You don't even get that. You've got enough impedance in your body, it doesn't hurt you. What if I tried that with 400 volts?
Yes.
You're dead. You're having a bad day, especially if you're a little bit moist. Touch some bare metal, right? There's no insulation there. So this system on that system seems like a really dumb idea. Poor, in fact, right? So this guy here, our red cable and our black cable, are part of what we're going to call a floating electrical system. It doesn't mean that we put it on the water and hope for the best, okay? Unless you're a boat maker, then maybe. What it means is it floats in the chassis. Ideally, what leaves from a positive cable has to come back to the battery on a negative cable. We do not use the body of the vehicle as a ground. We are trying to keep the positive and negative high voltage system isolated from chassis. Isolated from the chassis. Ideally, the resistance between one of the cables or one of the components and the body itself is infinite. Realistically, it's not, but it's a lot, right? It is a lot of resistance between the chassis and the high voltage electrical system. Why becomes the question. Why do I want this thing to be floating in the chassis? Why not just use the body of the car? Ryan, what do you think? Why not just use the body of the car?
The chassis of the car is metal, and then the body of the car is like made some like plastic and.
No, the chassis, body, I mean those interchangeably, okay? So I like your theory, right? Your body is metal or the chassis is metal. Okay? Why not use the chassis as a ground? Why not use that to get from the DC to DC converter back to the battery, or from the inverter back to the battery? Why not use the metal body, the metal chassis?
Would it be too much?
Too much current, you think? Burn the chassis down? I think there's enough metal in the chassis to take the current. Think about the size of the cable. and then think about the surface area of the chassis. So there's definitely enough room in the chassis to take the current. It's a redundancy, it's a safety measure, it's to make sure that you're safe. Even if you get into an accident, if you touch a high voltage cable, the likelihood that you're going to get hurt is pretty low, because what they want to see is, so we'll put our stick figure here, having a good day, got his finger up here, oh, touching that, and his other finger is down here, and he's touching ground. Put nice boots on, there he goes. Is he gonna get hurt? How come? He's to the chassis, but there you've got 400 volts of potential in the chassis. Is the chassis 400 volts? No. Is there a difference in potential then? So should electricity flow? Yeah, right? You're thinking, yeah. Is it? Hold on. How come I saw you say no, how come?
Because you have completed the circuit.
You haven't completed the circuit. It's not attached to the negative. It doesn't go back to the battery. So you can be a dummy, grab a live high voltage cable, and if you don't touch the other live high voltage cable, or if there's not an accident in the system, you're fine. That's a safety feature in the car. High resistance between the high voltage system and the chassis, or the body of the vehicle. You are gonna have a real hard time getting hurt unless you're willfully ignorant and trying your damnedest to make the circuit complete. My God, it just made it safer to work on these things again, right? Don't get complacent though. We can still hurt ourselves. Excavators, highway tractors. Are the drivers always careful and accurate in their daily inspections? No. We've all seen the news, right? The guy's like, I don't know why the wheel fell off. Well, the hub's still bolted on and the flange broke off. Yeah, it was fine when I left this morning. Sir, all the steel belts are hanging out. It wasn't fine. So we know that we're not going to get the best drivers. Say they're in a urban area, or not an urban area, a rural area, and they don't see the median. Are they going to drive their tractor across the median? Sure, seen it in lots. Been in a few of them. Oh, maybe the frame scrapes. It's an electric truck. That little guy right there, this little guy is what we're going to call a loss of isolation. That little guy means the high voltage system is touching the chassis. Now, you as a service technician, you didn't take your proper precautions, you didn't make your measurements, you didn't read the codes, you did nothing, you just hopped in this vehicle. You're like, I know how to fix this. You grab a high voltage cable, you grab it where it's bare, now you're touching it in the chassis, what's going to happen? That's the bright spot in our life, and soon it'll be a dark spot because it'll be like an ash and it'll blow out and everything else, right? So, the point of it is, the high voltage system floats in the chassis as a redundancy, as a safety measure. Whatever leaves the battery in a floating system on a cable has to come back to the battery in a cable. Okay? Does not use the chassis as a ground, and it is a safety measure. This loss of isolation thing, that can happen. It can happen in a few different ways. We can have mechanical damage on a cable. We can have groundwater or road water that enters a component, right? Salt water enters a component. Failures inside of the component. Just a circuit decided that, you know what, today's the day I'm going to go and touch the case. So loss of isolation is gonna become a real concern when you look at these systems. To the point where I've memorized the loss of isolation code outside of the battery. P0AA6, loss of isolation. If you ever get this code, it's not the end of the world. You're not gonna die. You're gonna take your precautions. You're gonna figure out where it is. P0AA6 is like a P0300 to you. What's a P0300? I think I heard it. What's a P0300? What's a P0300? Look at that, the brain's barely fired up. What's a P0300? Do you know? Multiple cylinder misfire, or random misfire. What cylinder is it in? I don't know. It's in a cylinder though, right? What cylinder is P0300 in? Who knows? You got your work ahead of you now for the day, right? You got to figure out each cylinder. What if P0300 is set with a P0302? What cylinder is it in now? 2. It says right there in the code, P03, okay, it's misfire, O2. Ah, misfire in cylinder 2. Okay. Are you going to go check cylinder number 8? How about cylinder 6? You're going to start right there on 2. P0AA6 tells you there's a loss of isolation. If it comes with a code that says the loss of isolation is in the inverter, are you going to go check the battery first? Wouldn't make any sense, right? If it doesn't set with another code that tells you where it is, you're having a bad day. Bad day. Terrible day. All right, let's take away the loss of isolation for right now. Let's take away our friend Sparky here. There we go. Get him. Rid of our loss of isolation and our AA6. All right, there we go. Get rid of that. I'm gonna fix that now. Hold on, I got my butt markers. There we go. There, perfect. How about here? Does the high voltage here connect there? That's a weird question, right? If this thing charges that, does the high voltage connect to the low voltage? How do I charge a 12-volt battery without voltage? Because I'm telling you right now, they don't connect inside that DC to DC converter. Man, the mysteries that we're going to solve here today, it's going to be like the Scooby Gang. Right? That's silly. That's the wrong color. That's the wrong color too.
This is the right one, yeah.
No. Better yet. Yeah, you're seeing it. IGBTs. I'm drawing them on a smaller scale, so they're smaller. There we go. I got this. There. IGBTs, right? Then we take it out, we put it in here. That's coil, right? If I put current backwards and forwards through a coil, I get a magnetic field that grows and shrinks and grows and shrinks and grows and shrinks and grows and shrinks. Moving magnetic fields create what? They do, they create electricity. Nailed it. So we're going to induce into another coil right here. And if you don't get all this today, it's on you. We're going to have that exam tomorrow. No, we'll be repeating this lots, okay? Goes through, we got rectifiers in here. Boom, we got one over here. Goes, like that, boom. There we go, they're gonna join up in the middle, so we're gonna have AC here, we're gonna have AC here. High voltage, low voltage, rectified, goes out. We got a little choke in there, dot, dot, dot. We got some, what do you call these things? Some of those, yeah. Capacitors, talk about them. There you go.
Now, in the DC converter, would that be a Zener diode in there?
Zener diode? No, it's a regular diode. It's just taking low voltage AC and turning it into low voltage DC. It works.
But that's DC to DC.
That's right. It goes high voltage DC to low voltage DC by making AC in the middle of it.
Oh, okay, I thought by putting the diode in there, the extra electrical would just go back into the system.
Nope, we can control it by how fast we switch it back and forth. That's what the IGBTs are there for, to control output. What's the matter? What's the question? Are we supposed to be here? No. But I got lonely and I'm like, you guys should come join me on Monday. I want to be here 5 days. You know what I mean? Look, I'm tearing up, I'm fake tearing. Is that good or what? I could be an actor. Okay. So, we figured out DC to DC conversion. Does the high side touch the low side? Inside that box? Nope, there's an air gap. That air gap is a fancy word. Ready for it? It's galvanic isolation. Yeah, I paid like $6 for that word coming in this
Repeat
morning.
that one more time.
Galvanic isolation. So this little space right here, that space in the middle, oh my God, I'll get down for this word. Galvanic isolation. Nailed it. It is the air gap that keeps the high voltage side away from the low voltage side. Oh, neat. So, we've now built a system, I think, pretty completely. What do you say? Do I need anything else in this system on the high voltage side to make an electric car work? Don't worry about recharging the battery yet. To make a hybrid car work, say a really simple hybrid car, like my Honda Insight that I've got downstairs. Did you see the little silver car that I've got downstairs? The tiny one that's like super old, and if you try and put a magnetic sign on it, it falls off because it's aluminum. Alternate materials, that's where it's at. Okay. Do I need anything else? Not really. Right? Don't worry about heat and cool. Kids worry about hot and cold. If I use a nickel metal hydride battery, throw some air over it, nah, good enough. So, do I need anything else? The answer is no. This is the most basic hybrid layout. Yeah, it's gonna pair to a gas engine somehow. In the Honda, I literally bolted the rotor of the motor onto the back of the engine. Now the rotor's got a place to live. Surround it with the stator. There it is. 3 cables come out of the battery assembly. They go to the inverter in that Honda. Right beside the inverter in the battery box, the DC to DC converter. There's a single red cable that comes out of that box and goes all the way down, 12-volt battery, wherever they're hiding that. I think they put it under the hood in that car. You know, you want your battery cables as long as possible. It's not true at all. So far so good. And then, of course, the battery itself is inside the battery. It's weird. All contained in a box, the whole system. We know how it's made. We know why. Let's talk about our testing, because we're technicians, true? All right. So, we're going to pretend the system is running. Should you test a system while it's running? Not usually. Okay, but for our argument's sake, we're gonna start off with easy stuff. We're gonna start off with voltage measurements. Ready for this? All right. Battery voltage. System's running. We go, hold on, oh, throwing my butt markers now. Here we go, we're gonna go from positive. We're gonna say the test points are at the battery. To negative. Boom. System's running, how many volts should I see? 400, yeah, right? Positive to negative, full battery. We're gonna see 400 volts. Yeah! There's test 1. Test 2, the system is properly isolated. It is not touching the chassis. See my quotey fingers kick up just like, bam, quote. It's not touching the chassis. So we're gonna go ahead and we're gonna test our positive. We're gonna go to the chassis. And what do you think you should see? Remember, it's not supposed to touch the chassis, right? So how many volts should you see? You would think, right? 0. Yeah, I love your answers. Totally, you should see 0. It's wrong. I like your attempts. But it's what you think. It's what you are trained to think, okay? And then on the other side, we do the same measurement. Yeah, I'm gonna tell you what we're gonna see. We're gonna go over here, we're gonna put it through a voltmeter, bam, and we're gonna touch the chassis. And what would you expect? 0, right? Everyone's okay with 0 so far. What are you actually gonna see becomes the question. No. Who said 400? You're fired. Get it? No. You're not fired. You can stay. $200 on each. That doesn't make any sense. It's an open circuit, right? Except we're dealing with modern cars and modern problems. Does this car have to know when it's on? Yeah, better know when it's turned on. Does this car have to know when it's lost isolation? When it's shorted to the chassis? Does it have to know that that high voltage has a problem to set code? Yeah, it sure does. How do you measure high voltage? What do you use? You use a meter, right? Multimeter. It's pretty easy. Doop, doop. What does a car use? Electronic multimeters, basically. It's got to, how do you measure voltage? You have to connect to the wires, right? How does a car measure voltage? It's got to connect to the wires. And then it's going to report the voltage back to a computer. Oh my God, the high voltage is connected to the chassis. Oh, bum, bum, bum. And it's usually connected to the chassis way over here. So we're going to blow the what's logic? It's a computer. So logic in that thing is just the inverter control module. We're okay with that? Okay? And then this one is a BFR. Not a real term. Big friggin' resistor. 10 million ohms or more, right? Huge resistor. What's the internal resistance of a multimeter? We measured it the other day. What? 4,000 million ohms is as high as the insulation tester can read. It's 10 million ohms is what we were finding, right? 9.98 mega ohms or whatever it was. So it's huge, right? The internal resistance of a multimeter, and that's how it protects you. So how do I protect my little computer from the high voltage circuits? Big freaking resistors. Same way that I protect you with a multimeter. Okay, so we got resistors, top and bottom. This resistor is the same value as that resistor. So for argument's sake, we're going to go 10 megohms, 10 megohms. Okay, just like that. And then the computer, where does the computer gets 12 volts from the 12 volt battery to run, and where does the computer return that current to? Because it's on the 12 volt system, right? So this little logic computer here must go to ground, right? Oh, so we're connected to ground, but we're connected to ground through incredibly high resistances. So those incredibly high resistances, are they going to allow lethal amounts of current to flow? No, we did the calculation in the lab. It's like through 10 million ohms, it's 0.00001, or maybe there's another zero in there. There's a lot of zeros, amps. So it's less than a milliamp, way less than a milliamp. That's not enough current to hurt anybody. So even if we have a short circuit, it's got high resistors on both sides, we do not have a lethal occurrence. But we do have to measure the voltage on either side in order to monitor the circuit. If the circuit's properly isolated, as we have here with that board, we will see half battery on the top, the other half the battery on the bottom. Because the computer sits exactly in the middle between the positive bus and the negative bus, grounds to the chassis, so that would be your intermediate. Let me bring it back to automotive basics, okay? Want to do that so this makes more sense? Because you're looking like you don't like this. You okay with this so far? Maybe? Let's do it. Let's travel. Let's go on a trip, shall we? We're gonna go back over here. So we got 12 volts at the top. Bam. 12 volts. Goes down. Yeah, it's got circuit protection. It's got, yay, who cares? We got a resistor. And that resistor goes down. Okay? Now, ready for this? If I measure from here to here, put on my old voltmeter, how many volts do I see? Through the resistor, it's a single circuit. How many volts did I lose across the circuit? One load in a circuit. 12 volts goes in, 12 pressures go in. How many pressures come out if there's one load in the circuit? I lost 12 pressures, right? So I would measure the difference in pressure, and it would be 12. It's 12 volts. If I measure from the top, but I only get halfway down, I got my handy dandy voltmeter there. How many pressures do I see lost over the first half? Say it loud. 6. So for the first half, I'd lose 6 volts because I have to save up 6 volts of pressure to get through the second half, right? So if I measure the second half, how many volts do I lose? 6 volts. How much was the battery? How much of the battery is that? And that is? Look, the computer sits in the middle of the resistor. And notice how I drew the ground here? Look, that's how it's making it back. See how I drew the ground here? It measured the difference between the positive bus and the middle of the resistor, because it got through here. That's how that worked. How crazy and cool is that? Weird expectations, right? Weird. All right, so. I think it's time to relax your brain again. Take another 10, grab your dart, we're gonna come back, we're gonna talk about what we're looking for when we turn the system off. The zeros that we're looking for. Remember, we already went through, the battery is not likely to hurt you. Something else in this system wants you dead, right? Cool. We'll discover that after our little break, okay? So go take 10, wander around, we'll see you back here.